Let us now invite our distinguished speakers from the session to exchange their knowledge and ideas, and I also invite Dr. Yusuf Wahbi to moderate this panel. One small keynote to our speakers as this panel discussion is beginning. In order for your microphones not to intervene or interrupt another speaker, make sure you place them on mute before you relay your message. The floor is yours, Dr. Yusuf Wahbi and everyone else.
Welcome, everyone. Thank you to our MC and all our speakers so far. Good morning, afternoon, evening, depending on where you're joining us today to attend this exciting and futuristic panel, I must say, to close our forum's first day agenda. I want to remind the audience to please use the chat box at any time to send in your questions. So building on the insightful presentations given by our four distinguished speakers so far, they'll be joining me to discuss the value of leveraging high-performance computing, AI analytics, and UAVs to advance rainfall enhancement research in general, and more specifically, cloud seeding operations. Again, our distinguished panelists include Mr. Talal Kaisi, Vice President of Strategic Projects and Space Program at Group 42, welcome. Professor Eric Frew from the University of Colorado Boulder, as well as Dr. Duncan Axisa, Director of Science Programs at Droplet Measurement Technologies, also from Colorado. And finally, Dr. Juha Tantila, a scientist from the Finnish Meteorological Institute. First off, I'd like to thank Mr. Talal for his insightful presentation on all the activities being done at G42 here in Abu Dhabi. And I'd like to start off with the first question for you, Mr. Talal. We all know that AI has been widely used in the post-processing and calibration of output from physics-based climate weather prediction models. But some argue that beyond post-processing, we've seen a lot of attempts that want to replace the physical parameterizations altogether and move into more AI-exclusive forecasts. So my question is, do you see the concept of exclusive AI-based climate or weather forecasting taking shape over the next 10 years? Or is a hybrid approach where we'd combine sort of the physics and the AI the most promising path for that?
Yeah, no, thank you for your question, Yusuf. I think it's a very important one. Not one I'm particularly the most qualified person to answer, but from the limited exposure I've had in this domain recently, I think a stepped approach and a sequential one at best would be needed. So, be it a hybrid initially, and then a more AI-driven one. The key with AI support of this type of an initiative would be the scalability. And I think we can get to that point quite quickly. And that scalability would allow for a lot more types of intelligence to be drawn out of the data that's ingested. So the more granular the data, the higher resolution the data, the better in terms of the predictive modeling, a supercomputer would be able to then support generating analytics for. So I think we're not totally there yet when it would be an exclusive AI type system. I think there is always in the near term going to need to be that human factor that supports and drives the generated outcome. But in the future, I think it's quite inevitable that the scalability of high performance computing would allow for predictive modeling to be done in a more automated fashion than is the case at the present time.
Yep, indeed, Mr. Talal. And we did hear the term data hungry a lot when one of the previous panels. So of course, that's a precursor, important precursor of making a decision on this. Right. My next question will go to Professor Eric. Thanks a lot for your presentation, giving us an update on the project, on the exciting use of UAVs. Besides the socioeconomic and environmental savings that are promised with the use of UAVs for, say, cloud seeding operations, one issue that comes to our minds is, are we there yet? So is current UAV technology capable of operating in severe weather conditions and storm conditions, which we usually target in our cloud seeding operations? So we're already in a turbulent environment. So could you maybe give us your take on this?
Yeah, thanks a lot. It's a pleasure to be here. I think Well, yes, I think the technology is here. I think that the fundamental limitation really over the last decade, we'll say, has been the logistics and the regulations and having those catch up with the technology so that we can really deploy systems in these environments at a regular enough pace to really refine the systems. I think the technology is there for teams who are practiced with it and are, skilled to deploy in these extreme environments. The technology is perhaps not there where you would simply purchase a system on the shelf for these types of extreme environments. But I do think that the unmanned system technology, the drone technology, is reliable. As with manned aviation, it's taken a long time to really refine our systems to the level of safety that we really want to see. And I think with drones, we can easily get there once we get these experiences and get the practice sort of under our belt. But I'm very confident that these systems are safe and robust and can operate as intended in these environments.
Thank you, Professor Eric. That sums it up pretty nicely. I'll move to your co-PI, actually, Dr. Duncan now. I personally know, and of course, many of those who are watching us today, that you were involved in many operational cloud seeding activities around the world, campaigns and field programs. So I'd like to ask you, based on your experience, do you think conventional cloud seeding flares should be replaced with maybe new delivery mechanisms that are more compatible with UAV systems, say like in Professor Refru's project, with their aerodynamics and the payload limitations we have in these emerging delivery mechanisms? And of course, seeding material release rates and concentrations are key in the question. Perhaps you could share some insights on this from previous experience and as you're learning through your project with Professor Eric, of course.
Yes, Dr. Youssef, thank you for that question. It is indeed a very important one. I think when it comes to seeding agents, there is no one size fits all. And this is because the hypothesis on which cloud seeding operates is that we are trying to introduce an engineered aerosol that in its concept operates based on the premise that it would be effective having knowledge of the pre-existing aerosol concentration, the pre-existing CCN number concentration and size, and the pre-existing ice nuclei concentration that is impacting the clouds. So engineering a flare or a seeding agent has to be done in the context of the environment of its intended release. I think that's a very important point. Secondly, the way it's packaged then would depend on the vehicle that is being used for its release. Traditionally, we have been using flares that are packaged in a tube because they are easily handled. They can resist deterioration because they are not prone to leaking moisture that would change the hygroscopic properties. And they are very operationally ready for deployment. That doesn't mean that we should use them widely without prior knowledge of this pre-existing CCN and IN knowledge of whether the material would be effective. In terms of seeding rates and also seeding material, some of the work that I did previously showed unambiguously, without any doubt, because we were able to put a tracer in the atmosphere and define precisely the seeding volume using a chemical tracer, that cloud seeding is effective when you release very large amounts of seeding material. So a very large rate was required. And this would depend again in the environment, but in the environment that we were operating in, which was convective clouds, we needed to release very high rates because the material disperses very rapidly within the cloud volume. So we have to really be cognizant about the environment in which we're releasing the material. Also, how the material is packaged is extremely important. And then identifying seeded volumes versus those that are not seeded in a very precise manner is very important to determine whether that material is effective.
That sums it up excellently. I couldn't have asked for a better answer. Thanks, Dr. Duncan. I'll now move to Dr. Juha. You shared a lot with us on the AI-based tracking of the clouds, etc. My question to you is more on the cloud microphysics. I know you're also working on that pretty closely with the FMI team. So as we all know, cloud microphysics refers to the small-scale, sub-micron computationally expensive processes that affect cloud and precipitation particles. Current microphysical parameterizations primarily rely on just two parameters, and that are the mass and the concentration of cloud droplet in our droplet population. So we call it generally a two-moment scheme. So my question is, how can we leverage machine learning to be able to reach higher order schemes and replicate more closely what's happening in the microphysical processes? So my question is, how do we reach maybe 3 or 4 or even 6 order schemes leveraging machine learning? And again, in my mind is that gap where we need the observations. It's a data hungry process. So how do you maybe align those two challenges together?
Yeah, I think this is kind of related to the previous discussion on your earlier question about should we replace parameterizations with the AI methods totally, or go with something intermediate? Then I would go with the latter. So basically, we would then have physical schemes based on fairly simple first principles, but we could use machine learning methods to bring in some of those additional details that we, for the foreseeable future, we don't have really a way to directly calculate because of the computational limitations. So in that sense, that would be probably the way to go with that. And of course, yeah, I mean, probably the availability of the observations is I would say even a limiting factor there. So that's something that would need to be increased to make that happen, I would say.
All right, I'm just going to throw a keyword out there that I've been hearing a lot nowadays. It's about CubeSats. Maybe Mr. Thal can allude to that in the later part of the discussion. I think those are being used in a lot of fields, and they're quite relevant for gathering those in-cloud measurements that are so precious to our models in the microphysical processes that we want to simulate here. Back to you, maybe Mr. Talal, navigating back to some points I raised before. A lot argue that when we go with machine learning algorithms to sort of resolve the physical processes, we might violate these physical laws in the sense that mass or energy conservation, or even we may fail to construct unseen conditions such as extreme weather events in this specific context we're discussing in the forum. But this is also a general question for all applications which AI and machine learning is being used for. So that said, there's always this black box stigma that's associated with AI, and a lot of research is now going into explainable artificial intelligence. So my question is G42 attempting or planning to help whiten this black box stigma that's associated with AI, or maybe you could share some future plans if that's not already being done?
Sure. Yeah. No. Very much so, Yusuf. I think as I explained in my presentation, we have the Inception Institute of Artificial Intelligence that's always looking at the cutting edge fundamental research, and now we're looking at ways that we could translate that into commercialization and applicability. And this is a key pain point, obviously, in trying to sell, quote unquote, the benefits of employing these types of methods to big and hard problems. And you're right. I mean, there are certain blind spots and black boxes at the moment, especially when you can't really kind of think of every single different scenario. But that's where, you know, the simulations come in. That's where the amount of data and time that goes by will improve and iterate on those processes to get them to where they're more optimized and can support the various use cases that we look at. You know, in fact, one of the questions that you asked Dr. Duncan is a very interesting example here. If you're looking at different types of materials that could be used or substances for seeding operations, there's no better way to do some novel material research than going through a large number of simulations and exploring the efficiency. And you can only do that effectively and at scale with thousands of parallel cores. And that's where kind of, having the cloud compute infrastructure as well as our HPC provides the ideal environment for such experiments.
Indeed. Before I move to the audience questions, I'd like to check if any of the panelists has anything to add maybe on what we've discussed so far. Please go ahead, feel free. All right, I'll move to the first audience question addressed to, I'll keep this addressed maybe to Dr. Duncan and Mr. Talal. Feel free, whoever wants to go first on this. It came from Professor Martin Umbum from the University of Reading, the UK. He says that AI solves data problems, but are the problems related to data processing or related to physical understanding when it comes to cloud seeding operations? Maybe Dr. Duncan, you want to go first on this since you're more experienced with the cloud seeding field in general?
Sure. I think going back to the very first slide that I showed of this AI maturity curve, when it comes to rainfall enhancement operations, we are not making good use of data. So the data is dark, it's there, but it's not made available to the operator. We have very good models that are predicting areas where to seed, for example, maybe a couple of days in advance. Or we have highly instrumented aircraft and very capable radars and other remote sensing capabilities. These data are dark to the operator that is conducting the operations. Yes, we have a meteorologist that is assisting and talking to the pilot. There is a time lag of communication and the time lag of information there. So we can do better, actually. And this is why we need to put a program in place to make these data more accessible, where they provide insight to the operator, which could be the person on the ground or the person doing the operation, so that they can act on it. So that now elevates the level of an intelligent system from this L2 to L3 level, where you have data that is immediately actionable. And in order to move now to autonomy, which is the L4 system and what Professor Eric Frew is working on, then that data has to have a higher level of AI. But we are so stuck in this dark data phase and focusing a lot of our research on improving these tools. Yes, it's good to improve these tools, but they can't remain dark to the operator.
Indeed. Thank you, Dr. Duncan. Mr. Talal, would you like to add anything on this?
Yeah, as you rightfully mentioned, Dr. Duncan's a lot more well-versed in this area than I am, but I did pick up on a couple of points he made that I think might be something that I could chime in on. So, Dr. Duncan mentioned time lags, and I think one of the things that I believe, at least with what you mentioned, Yusuf, earlier in terms of CubeSats, is that we are going to have the level of density in low Earth orbit with CubeSats because of the new accessibility to space that, both low-cost launch as well as miniaturized technologies and more of a plethora of companies realizing the benefit of creating low Earth orbit constellations is going to have. And that, in effect, is going to increase the revisit times where you'll get near real-time data to then induce the accessibility of actionable insights. So I think that's one area where you have to have both sets, the hardware and then on the AI side, the ability to make sense of that in near real time to produce actionable insights for an operator to be able to conclude certain decision-making operations with.
Indeed. My next question, and maybe the final one, because we have a little bit over time. I don't want to keep everyone. I know it's just morning now in the US. So my final question came from Dr. Roelof Prinsjes from NCAR, National Center for Atmospheric Research in Boulder, Colorado. And he was asking Dr. Juha, how do you treat ice formation in the model based on the Rhine growth being so important in the seeding, as you noted?
Yes, so our modeling approach for the ice basically follows the same idea what is behind the P3 microphysical scheme, if you're familiar with that. So basically we have separate tracers for unrimed and rimed ice because they can be separated in terms of the processes that create them. And for ice formation, we use like these parameterizations based on the classical nucleation theory. So that part is pretty simple. But then we have these separate mass tracers for the different types of ice within the size bins for the ice particles. So we can then get the mass fractions for the different particle types.
All right. Well, I'd like to thank all our panelists today for making the time to join this interesting session. I see a lot of diverse backgrounds, and it's definitely the way forward to improve the field of weather modification in general. I just want to urge everyone to attend tomorrow's session to dive deeper into the innovations in weather modification research and where it stands within the bigger picture of climate change. Again, thank you to everyone who participated today, and of course, our distinguished panelists that joined me in this session. Thank you very much, everyone.